Hey everyone. So today I'm going to be demonstrating a very simple zero knowledge application. And it's going to demonstrate the usefulness of zero knowledge. The idea really sprung from a Twitter post that Alyssa Tech made on Twitter. Um, and I was very intrigued by the idea of doctor's notes and how to preserve privacy while indicating that you're sick. In particular, when you give a doctor's note, especially if you have a very specific ailment, you can leak the specialization of the doctor, and through that, you can leak your ailment. And so a zero knowledge proof is actually a really good way of proving that a signature was made by someone like a doctor without necessarily giving details of the doctor that can leak information about your ailment. The way we're going to do this is we're going to set this up as a ring signature, but we're going to set up the ring signature through a zero knowledge circuit. So it's not necessarily a traditional specific zero knowledge proof specific to a zero knowledge circuit. We're going to use something based off of what they call Plonk, and it's called Mina's ZK app programming. It's built in Snarky.js, which is a super or subset of TypeScript, so really easy to follow along. The idea here is going to be that we have a variety of doctors, let's say a dermatologist, and a neuroscientist, or a neurology doctor, and a variety of other doctors that are in the world, right? And one of these doctors with a specialization has provided you a doctor's note. And we can represent these on a ring here. Usually in mathematics, they represent these ring signatures as a ring. So I think that's where the name comes from. I'm not 100% sure. But essentially, let's say you have these specializations, right? So you have a dermatologist here, dermatologist, and then you have, let's say, a neurological specialized doctor. I don't know what they're called. You have these variety of different doctors, and you want to ensure that one of these doctors has signed your doctor's note. But you don't want to actually tell anyone which of these doctors has signed it. Now, in Ontario, we have something called the CPSO, which is basically just a association of surgeons. And what they will represent in our program is a trusted authority that can ensure that all of these X's, which represent public keys, which are these cryptographic sort of representations of these individuals because of the fact that they hold a very specific piece of information that represents their identity. Um, and so you have what these things called private keys and public keys, but each of them have separate private and public keys. But what we'll represent is we'll do something called a signature here, and we're going to sign this doctor's note with a particular doctor. But then when we try to prove that that signature was made, we will prove it in a generalized way that proves that the signature was made by one of these sets of doctors. And the proof we're going to generate is not actually the signature on the doctor's note itself. What we're going to generate is the proof of the snark, which is this non-interactive protocol that's going to occur where we're going to have automatically our system taking this TypeScript code is going to set up this thing called a mathematical circuit, and it's going to create something called a snark, which is basically a sequence of arguments across two types of people, a prover and a verifier, and they're going to generate this proof or receipt of interactions, which will represent the idea that when you show this proof to someone, it will be deterministic and provable that you were able to get a signed doctor's note from one of these individuals with one of these specializations, but you're not going to leak the actual information. So that's the preamble and the theory behind it. Now we're actually going to go deep into building this out. So let's just start here. I'm just going to clear this. And let's say we want to build a project, so let's do ZK, which is the ZK app CLI from Mina protocol. And then we're going to do the ZK program, and we're going to give it a name. So for this, we're just going to call it Doctor Note. It did not work. Okay, let's see if ZK itself works. Okay, ZK project Doctor Note. Okay, I was using the wrong command. That is okay. And now we have this here. Let's just open it in VS Code. Okay, and we have this open now. Now what you can do is in the source file, you have this add.ts. This is going to be where your smart contract is going to live. We won't rename this for now, but you can definitely rename this code. There's no real need to rename it for us right now, so let's just continue ahead. We're going to delete these little fields because we don't really need any of this. What we're going to be doing is slightly different. And so let's start with setting up this thing called a Merkle tree. Now, what the Merkle tree will do is actually, let's go back to the theory here. So, a Merkle tree is essentially something resembling a tree structure, but also having a lot of signatures and being very cryptographically heavy. And the reason for that is because with these signatures, it can provide some very strong guarantees around inclusion into a hash, or you can selectively prove that data within a piece of text exists within this piece of text by showing a set of hashes that are very compressed in nature. And so it's a way of compressing uh, provability of inclusion of data within a large corpus of data. And so we're just going to make a really simple Merkle tree here. And we're just going to use a size 4 Merkle tree. It's a very small Merkle tree, so it won't be able to hold a lot of data. Most often you'll see Merkle trees that are much larger because the core data is really here. In these last leaf nodes is where all the data is going to be stored. And so because of this, you don't just want a height of 4, which is going to be 2 to the 4 minus 1 in size, which in this case is, as you can see, 2 to the 4, 4 minus 1, which is equal to 2 times 2. Oh, sorry, 3. Height of 3. Minus 1, which is just 2, so it's 2 squared, which is 4. And as you can see, there's 4 leaves here. Now, if you wanted something much larger, you'd usually go for like 2 to the 18. But for this simple case, we're just going to use 4 as the height of the tree, or 3 as the height of the tree, sorry. Actually, we could do 4. I'm actually going to end up doing 4 in the program, but let's leave it for now. So you have this Merkle tree, and what this Merkle tree represents is a set of leaves which have pieces of data. So D1, D2, and you get the point. So in this case, it's just up to D4 because it's a height of 3. And then what this is going to represent as it goes up is, let's just keep it as lines. Okay. This is going to be a hash of D1 and D2. So it's going to represent the hash of the left leaf and the right leaf. And this is going to bubble up. This is a very powerful construct because it bubbles up. So you have now here the hash of D1, D2, which was the value here. But you also have the value on the right side. So you have the hash of D3, D4, and realistically, this is a very concrete representation of this. You can abstract this away to just be right node, right child, and left child, and the hash of the right child and left child. And now what you can see by this is that all we really ever need is this value, which is the right child, and then D1 hash D1 D2 D2, and this root hash to determine that one of these pieces of data is in this Merkle tree by just committing to this value h, the hash of the left child and the right child, to a particular publicly available location. And as these trees get much, much larger, this is really helpful because you don't need the entirety of the Merkle tree to be able to prove that something is included in the Merkle tree. All you would need is 2 pieces of data. So now that you know what a Merkle tree is, we're going to add it here, and we're just going to call it class Merkle witness 4, and we're going to extend this off of the Merkle witness that's provided by Snarky.js. So we're just going to keep it as size 4, and it's not going to let me Merkle witness. So we have a Merkle witness now. Now what we want to do is we want to see which types of functions we want to add to this smart contract, which is going to represent the state of doctors and the state of a doctor's note. So first what we need is to initialize everything, and we're going to do that in a separate method called init state. And for purposes of speed, I will simply pass in some code that I've already written. And we're going to get that that's a public key. So we're going to walk through this function now. The CPSO public key is the public association of doctors, and we're going to pass through the public key of that institution and set it publicly so that we can verify after when doctors are added into this method called, we're going to call it add doctor. And this is just going to add doctors to the Merkle tree that we have above. And so we want to be able to ensure that only a trusted association is able to add to that tree. And that is why we're committing it in the initialization of the contract. And then we have the root of the tree, which is going to be, which hasn't been written yet, but it's going to represent basically the tree root that we showed here. So let's go ahead and do that. Let's start putting in some of the code. I'm just going to copy it for now because of speed, and I don't want to bore you with the details. So now we have, and we don't need the initialization function, simply because we're going to call init state when we deploy the contract. So now you have add doctor, you have the init state, and let's go ahead and add some of the code for the add doctor portion. So we have that we want to ensure that at the beginning of this add doctor invocation, the only person that's able to invoke this function is the one that has the associated CPSO public key. Now, anyone has the public key because this is a public state variable, which means that this is made public within the Mina ecosystem. So what we want to do here is we want to actually take the private key of the CPSO to ensure, and that's basically secure. The security model there is that the fact that they have the private key means that they are the person. So we're basically proving their identity based on the knowledge that they have that is very personal and private to them. And we're going to keep this as a variable called private key, which is a class here. We can import from snarky.js, which again is the TypeScript superset or subset in a way. It expands on JavaScript and TypeScript, but it is slightly different in its ability to compute because of the fact that, and I'll delve a bit deeper into like Plonk and how zero-knowledge circuits work, but basically because the way this is getting compiled or transcompiled is not inherently meant to be running on a computer, but rather to be this mathematical prover verifier sort of interaction. The entire model of computation that you have to think about is entirely different from traditional computing. And that does require a bit of mental flexibility. For now, I would just follow along. If you're very interested, David Wong has these incredible videos on Plonk and the fundamental systems underneath what O1 Labs has built. So I would definitely go there and look at those. But for now, let's just continue on. So we have this add doctor, and as you can see, I have Copilot, and it gives a great deal of very useful indications, but let's not use that, and let's just go ahead and print what code I've already written for this particular function, just because it's going to be easier for me to walk through. So here, what's happening is we're passing in the witness, which is that representation of these hashes. So a witness would be, hash LC RC, and then RC, because the right child needs to be there to compute this value plus this value equals that value. And then we have hash of D1, D2, and then we have D1 and D2. So this would represent a Merkle witness in the sense that with all of this, what you can get at is you can prove that if the root is this, then B1 is within this Merkle tree. And that inherently, this entire little thing represents the Merkle witness. And as you can see, the Merkle witness scales to the height of the tree, which is very unique because it does not scale linearly to the amount of data in the Merkle tree. That is 2 to the height. So that's a very powerful performance improvement in figuring out if data is included. Then we have this doctor that gets returned, not necessary, but I'm just gonna actually, let's not return doctor because I've written the code to return this, but I don't think it's needed because the proofs we're going to do are unrelated to this. So, and then we have leaf witness.calculate root. Why is this complaining? Let's see. It must be, so leaf witness that's being passed in is not correct, and that's because we haven't described Merkle witness for? Have we not? We have. Okay. Let us discover why issues spring up. And I think that's a powerful and important part of building ZK apps is understanding how to actually debug them. So it says calculate index does not exist on type Merkle witness 4. So why would that be? Well, what is leaf witness? Leaf witness is that we have this. So let's see what Merkle witness has and why that is complaining. Let us pause for a sec. Okay, so I think I've figured out why that's occurring. It's because I haven't done npm install, which hasn't installed snarky.js, which is its own separate library. So let's let that complete. Okay. Does that solve things? Yes, it does. Okay, we can move forward now. So as you can see here, we have a committed public key, which we're getting from this public key that we had set in the initialization of the state of this application. And then we're asserting it. Now, Mina actually thought a bit about why and if to include this sort of forced assertions of every piece of data that you would get. And Mina decided to keep the assertions. And I think I agree in some part with why they did it, because you want to keep in mind that these programs are not necessarily being computed, like compiled just in time or being interpreted by a JavaScript interpreter. Inherently, what they're representing is a circuit, and these circuits require assertions because the entirety of this sort of very abstract zero knowledge proof and the toolings that are provided to you by the proof system and the ZK apps that you're provided with are really around making assertions about data. What you're doing is you're turning these programs into these very mathematical representations, and then you're asserting some mathematical equivalency or some sort of mathematic formulations on intermediate values through the execution of this program. And I think it's a really useful way of looking at how zero knowledge proof in this particular compute environment works without necessarily needing to go very into the nitty-gritty details of Planck or some sort of modern arbitrary snark sort of engine or proof or scheme or proof system. But if you want to dig deeper and deeper, there's more mathematical formulations. This all gets represented as like polynomials, and it gets much deeper. But at a general sense, what you really want to grasp is the idea that there are intermediate values that you want to make assertions about through the execution of computation without revealing the entire execution of computation. And that's where these zero knowledge proof systems really become powerful, is their ability to allow you to do that. So in this case, we want to make these assertions that this committed public key is the only one that's able to execute within this piece of code. And the reason we want to do that during execution time is because we want to ensure that a credible person is constructing this set of doctors. So any third party that wants to, like your employer, if they want to be sure that your doctor's note is authentic, well, what if anybody, including yourself, could get your parents and friends and whatnot, or your 2-year-old child to create a little public key and post it as if they were a doctor and then sign your key for you? That would not make sense because you're not a credible person. So to restrict this set of data being constructed to only an association like the CPSO would facilitate that level of trust. And so we're going to make this assertion that they're the only ones that can come in and execute these additions into this Merkle tree. And then, as you can see here, um, you have this assertion, which is what I'm talking about. This assertion, sorry, was just to get the public key and verify that the public key you got was the correct public key, and that goes back to the idea of these programs often need to find equivalency uh, between variables that are accessed, and to equate them to themselves is very important because that's fundamental to the representation underneath this that it transcomposes to, which is a mathematical circuit. Um, and then over here is the main assertion, which is that we're asserting that this committed public key that is a public state in the MENA protocol is also the public key that is derived from the private key which a doctor owns. And then we move on to getting the initial state of the tree itself, which we would need because we want to ensure that we have um, the correct tree at this moment. And then we calculate the next index. And the next index, really, what it represents is, let's say your last index was D1, then your next doctor entry would want to be in D2. And if your last entry was D2, you'd want it to be in D3, and so forth. Um, so we get that. And then we calculate the new root by, so we have doctor.x here. What you would want to do is Poseidon hash. I'm not going to get into that just to make it simpler, but really you would hash the public key of the doctor and store that, and then you could later on rederive it from that hash. But we're just going to keep it as doctor.x for now for simplicity's sake, because this is already getting a little too complicated. And then you have to set the new index, which is going to be the next index, and you're going to set the next index to, or you're going to set the current index to the next index, and then you're going to set the next index to one added to the current index, which means that the next time someone comes in, they're adding to the next tree element. And then we can create the verification of the SIC note. So this is the important part, really, where a person, a common, or like a patient with a job will come here and execute this function and provide the proof to their employer. So you have a doctor witness, which will represent where this doctor is in the Merkle tree. So if the doctor's name is like here, you would want that path to here to determine that this root tree that has been committed up here includes the doctor that signed your note. So that's why we're including the doctor witness here. And then following that, you'd want the doctor's public key. Just a public key. And then you'd want a signature. Okay, I'm just gonna add that here. Okay, so, and the signature also needs to be imported from Snarky.js. And the signature is really going to represent the fact that the doctor signed your name saying that you are sick or you are their patient. And then the patient public key is important because the patient public key is the thing that the doctor has signed. Yeah, okay, so let's move forward from there. And now we're just gonna copy it again. So here, this root.assert equals, what we're doing is we're asserting that the true root is equal to the root that exists within this doctor witness. Again, what we're doing is we're taking a witness that at the very terminal end includes this value D1, which is the doctor, or DI really, arbitrary doctor, and we're sending this entire proof all the way to the top root proof. And then one can compute D1 equals D1, HD1, D2 equals the values that you have in your Merkle witness, and then all the way up to the top to ensure that the doctor that you are talking about is included in there. And that's what this process is really doing, is asserting that this doctor exists in this Merkle tree that we have enforced can only be added to by a doctor association. And by this point, we've proven that whatever doctor was passed in as a doctor public key is a real doctor. And then the second step that we're going to do is we're going to make a verification on the signature, that the doctor made. So we take the doctor public key because we know that this is a doctor node, that that's their public key. And then we're going to check that the patient public key, the signature that was passed in, truly is like the patient's public key, which was signed by the doctor, and what the signature represents, truly is correctly done by this doctor public key. And then we do an assertion that this is true. And invoking this as a transaction and proving it will facilitate understanding that this whole process went through correctly and that they truly do have a doctor's note from an authentic doctor. And then here comes the fun part. I'm just gonna write the new code here already. So here what we're doing is we're setting several doctors, so a doctor of cardiology and a doctor of dermatology. And then we're creating a witness of just a basic tree, the first node, and we're setting that leaf node. And we're sending this transaction to Mina. Mina is currently just going to be a local node that's running. We're not going to deploy it to Berkeley Net, which is their test net yet. And then we have our deployer key, which is just the key that we're using to represent the CPSO. So the private key of the person deploying the smart contract in this situation just happens to also be the private key of the CPSO. But obviously, although the CPSO could actually deploy the smart contract, it would be a very reasonable thing for that association to be the one that creates this contract and then distributes those public keys to the doctors outside. And then you have the cardiology doctor's public key, and we have a witness which represents that on the 0th leaf node, we're going to place the doctor of cardiology there, and then we're going to do a transaction.prove and then transaction.sign with the deployer key to send that off to Mina. Now, interestingly, transaction.prove is what's going to generate a proof. Now, and then the Mina protocol will sort of do the verification of this proof, and the proof itself is that representation of the interaction between approver and verifier itself, because what it represents is the completion of the circuit that represents the zero knowledge proof, and then you send that proof off to Mina. And then we have a tree here, and we just get the root of that tree, which is our initial tree. We set the leaf locally. So one thing to remember is that these trees, these Merkle trees, will often be kept locally because you don't want to be sending the Merkle tree itself and all of its data out publicly, because that would remove the privacy component. So you would want to keep this Merkle tree very private. So if the CPSO, for example, had this Merkle tree and they were adding doctors to it, they would want to be very careful about how they secure this tree, because there is that level of counterparty risk in this particular situation where if that association became malicious or was hacked, there is still a lot of security vulnerabilities to this protocol. Doesn't always have to be the case, isn't always the case. Zero knowledge proofs are actually a very useful way in preserving both privacy and security, but in this case, that is not a provision that you're given. What we're trying to do is just create a very creative method of a doctor's node. And so, as you can see, we set the leaf here, we set it to the public key. Here we're just going to do .x because, but usually you would want to do like a Poseidon hash of this doctor's key so that you can't just it just makes it a lot simpler to just hash the public key itself. And then we're going to make sure that the tree node is equal to the current tree root that we got from the application after this transaction went through. And that sort of shows that this application is running correctly. And then we're going to add another doctor of dermatology. We're going to add it in the second index, which in computer science represents the first index because indexes start at 0. And then finally, we have this new tree root, which represents these two doctors in this tree. And then what we're going to do is we're going to do the really important part, which is over here. And that is to say in this case that you went to the dermatologist. And if you went to the dermatologist, you would have but you don't want to leak the fact that you went to a dermatologist. So here, what you're going to do is you're a patient, and this is your private key, and the dermatologist is going to sign your public key so that the doctor can confirm that they saw you, and then you're going to send the Merkle witness, which represents where this doctor exists in this Merkle tree, to this smart contract or this particular zero knowledge proof to generate the fact that this user truly did, or this patient, sorry, truly did go to a dermatologist because the dermatologist signed their public key. Now, through all of this, once this is executed, it proves it and it signs it, and then it sends it off to the MENA local blockchain, which does another verification to ensure that this proof was generated correctly. And through this, what we've created is a ZK app that can provably ensure that to a third party like your workplace that you were sick, you have a doctor's note, but at the same time, you do not leak the fact that your doctor was a specialist in dermatology. This could be expanded to much further. For example, things like when was this doctor note created? How long is it valid for? For example, if you wanted a doctor's note that specifically stated how long you were sick, you could put that as part of your signature. Verify that on this current day, I am sick, as this signature states, from date X all the way up to 5 more days beyond date X. Patient X is incapacitated and cannot work, and they can provably do this with this platform. And so we've built this incredibly powerful mechanism of creating a ton of privacy for users in just about 20 or so minutes. And that's really the power of ZK apps, zero knowledge proofs, and this brand new technology that came out in about like 2018, 2019 is revolutionizing, I think, a lot of different spaces. And it hasn't seen much commercialization, but I'm excited to see it in the future. And I hope people join in getting interested and learning about these different mechanisms of computation.